what we like, right? We like animals. And animals tend to work in real time, although you guys went to Dinosaur or whatever, and that's kind of cool. And so I think there's something just inherently interesting. You know, you don't need to know anything about a bear to just go, wow, that is really neat. That's a bear. I could sit here for an hour just watching that bear eat acorns, and I'd be entertained. Whereas geology, I don't know, I might be hard pressed, at least initially, to go, wow, that rock, whoa. You know, can you imagine sitting there for an hour? So, so there's a couple things that happened to me that kind of made me see the geologic light, so to speak. And one of them was a book. I was working in the visitor center. This was years ago. Wintertime, this is a totally different park. It's very dead. And so there's nothing to do in the visitor center except read. So I picked this book up off the shelf, and it's called Assembling California. So, and it's the geologic story of the state. And I started reading that, and luckily it was written by this guy, John McPhee, who can make cardboard interesting.
I'm reading one of his books.
Are
right
you?
now.
Which one?
Annals of the Former World.
Oh.
So it's basically North America, the history of the geology of North
Oh my God! How long has that been out?
At least a couple years, but I don't remember what year it
I need to check that out.
Yeah, it's really thick, but it's really good. It's very interesting.
Okay,
He's
well,
a great writer.
Exactly. It was what kind of hooked me. Was his great writing.
Yeah.
So anyway, he's interviewing this geologist, and he asked the geologist, "Hey, you're the expert. How would you sum up geology?" And he said, "I can sum it up in a short sentence. The summit of Mount Everest is made of limestone." And you know, I had to think about it, but then he goes into it. Now, are you guys all geologists? Do you know how limestone is formed? What is limestone?
How would you explain where limestone comes from?
Oh, I don't know.
You live on top of a whole bunch of it.
I mean, it's a layer, right, that's been pushed up.
Yeah, so that's how it got to be Mount Everest. It got pushed up.
Yep. It was coral. Limestone is fossilized coral. So that kind of tells you a lot right there. You know where coral is made.
Right.
So, so that is a very telling statement, obviously, as it pertains to geology, because so much of geology is about plate tectonics. So, how do you get that oceanic rock to cap Everest? Well, the answer to that is the story behind the Sierra Nevada, and that is plates colliding. So, try to imagine 200 million years ago, the plate that was underneath the Pacific Ocean was colliding with the North American plate. That plate was known as the Farallon plate. And, sorry, that might look even better. That plate was subducted. That's the key word. And even though I'm not a geologist, I did take geology courses. And the most memorable lecture I attended, I walked into the classroom one day, and then there on the blackboard in bold letters was "Subduction leads to erogeny." And not knowing anything, I thought, this is some interesting things. Subduction, one plate sliding underneath the other. This plate partially melted. That molten rock started to upwell underneath the pre-existing crust. That caused not only volcanoes, but a mountain range to be formed. Some of that molten rock exploded through the Earth's crust. Much of it cooled and crystallized underneath 3 to 5 miles of the Earth's crust. So everything that you're looking at right now, like right behind us, there's still a little water coming out of there. You've got Yosemite Falls, just down the canyon, you've got El Capitan. Think about this. 3 to 5 miles of rock capping all the granite. That's what you're looking at here. It's mostly granite or granitic rocks. Quartz, a couple different types of feldspar. Those are the lighter minerals, darker minerals, mica, hornblende, that. It's taken tens of millions of years if this is the granitic rock that was emplaced, it's coming up, it's causing an uplift of the mountain range. Here's your 3 to 5 miles of rock capping all this granitic rock. It's taken tens of millions of years for this to erode away, finally exposing the granite that you're looking at. Now that story, I'm painting in very broad brushstrokes here. Some geologists believe that there's been one uplift of the Sierra Nevada mountain range. Some believe there's been a couple of uplifts. I will leave it up to the experts to debate that. But one way or the other, you've got uplift, and that uplift is a product of the subduction. Another word for uplift is orogeny. So there's the subduction leads to orogeny. When that uplift started, of course, the river that you guys have seen. Have you guys been in the park for a couple days, or did you just get in? Okay.
And we stayed up at Tuolumne Meadows, that area.
Oh, nice. So, yeah, both the Tuolumne River did the same thing as the Merced River. As this landscape has been uplifted, it started to flow faster, and that river started to carve a steep, deep V-shaped canyon. When you look at Yosemite Valley, you'd be hard-pressed to describe this. Well, the walls are steep, it is deep, but it does not have a V-shape. And of course, that's what we need to reconcile. If we know this, that these plates subducted, causing the uplift of a mountain range, causing the river to carve a steep, deep V-shaped canyon, why don't we have a V-shaped canyon? So that's what you guys get to meditate on for a little while we walk. And we're going to walk out into the meadow, and then we'll try to answer that question. Before we do that, are there questions or clarifications up to this point?
I think so.
Okay.
This is great.
All right. Okay, so I left you with this idea that we don't have this V-shaped canyon, and we did at one time. What happened to it? So, any ideas what could have caused that V-shape to disappear? As if you didn't know. What's that?
Uneven erosion.
Okay, and what could be a major erosional force?
I was thinking like softer minerals, maybe easier to wash out.
Sure, yeah, and that definitely has happened. You will find some limestone outside of the park around here, and we've got some marble in the park that you can find that where that's true. But what I'm talking about is a erosional force that is so powerful that it acts in very short. It's so powerful that it changes this rock in a relatively short geologic time.
Polished rocks.
Oh, that'd be glacial.
You got it. You got it. So, give you guys a little appreciation for this. Here I have a depiction, an artist depiction of what Yosemite Valley would have looked like prior to the uplift. So once again, I'm talking in generalities, but I think you can appreciate just the fact that this mountain range was uplifted. And a lot of analogies are used for that. Think of, the one that I like is, think of the Sierra Nevada resembling a giant trap door that's been half opened. So the western slope is gradual, the eastern slope is steep. If you imagine where my fingers overlap, this represents giant cracks in the Earth's crust, what we call bounding fault zones. And because of that, when this magma came up, it made sense that it was going to break off right here. That uplift caused the rivers to flow at a much faster rate, carving that steep, deep V-shaped canyon. And then, starting about 2 million years ago, global temperatures cooled enough so that glaciers formed. So imagine if my arm represents the western slope and the uplift occurring over millions of years, this river here is going to start flowing faster. Right now you see it's just gentle rolling hills. You've got big meanders. When you do this, that river starts to flow faster, and it starts to erode that canyon at a faster rate. And eventually you get something like this. This is what Yosemite Valley would have looked like roughly 3 million years ago. So it doesn't look anything like it does right now.
Yeah.
We've got, well, yep. Just see if we can see it. So another, whoa! Whoa! Hello. Another Stellar's chick. Man, this is my day for Stellar's chick. Okay, so any ideas what caused that ice age? Do you know what the prevailing thought is? How the ice age came to be?
Distance between the Earth and the Sun? Is
Yep.
that- Okay.
Yeah. So it's basically an astronomical theory, and this is not the only ice age that the Earth has experienced. There's been multiple ice ages, but this is the most recent. The Great Ice Age, better known as the Pleistocene, is the most recent ice age that the Earth has experienced. Massive ice age. There is something called the Little Ice Age. We'll save that for another time. But so distance from the sun, and there's also a couple other things, and that is the tilt of the Earth has changed over time, and then the Earth has also experienced this wobble, precession. And all three of these are known. Do you know what this is? Have you come across the Milankovitch oscillation? It's a
Okay.
mouthful. I wouldn't expect you to.
I haven't seen that before. But
Okay, so this is huge. This is a big thing because it explains. It's one of the explanations for natural climate change. So, and the tilt of the Earth changing, the wobble effect, and the shape of the Earth's orbit around the sun, all three of these things are on cycles. And the shape of the Earth's orbit is on a 100,000 year cycle. The tilt of the Earth roughly is on a 41,000 year cycle. And just to make sure we're all on the same page, the tilt of the Earth, basically the angle changes, the angle that the sun's rays hitting the Earth changes. So you could go from a more direct hit to a more glancing blow. And that's why that's important. And that wobble or precession is basically the same thing. So you have a 100,000 year cycle for the shape of the Earth's orbit, a 23,000 cycle for the precession, and a 41,000 year cycle for the tilt of the Earth. And if you meditate on this for a little while, eventually you ask the question, well, couldn't you synchronize these cycles? Yeah. And the answer is yeah. And then you can make for a more profound effect. So, and that profound effect is a cooling of the Earth's climate. So that glaciers started to form where you guys are camping right now, up in Tuolumne Meadows, up in those bowls, or cirques, as they're called. And to get glaciers forming, normally California would not have any sort of glaciers forming this far south in latitude. But because of the high elevation, thanks to the uplift of the Sierra Nevada, we've got the right conditions for glaciers forming. So there's a great book that we have in the Visitor Center called Glaciers of California. And the author of that book, Bill Guyton, calculated for glaciers to be made in the Sierra, you need to pile up about 1,200 feet of snow. So it kind of changes depending upon what part of the world that you're in. But once you have 1,200 feet of snow, Evan, how tall are you? Close to 6 foot?
close.
Yeah, close.
Okay. So imagine how many U's it would take to make 1,200 feet. Once you have 1,200 feet of snow piled up, the bottom 10% of that snowpack there's so much weight, the snow crystals basically meld together, they cinch it together, that forms ice. That ice collapses underneath its own weight, and voila, you've got a glacier. So this is Yosemite Valley, roughly 1 million years ago. This is Half Dome right here. And
Wow.
this is kind of an interesting story in itself, because as you can, this is our most expansive, our biggest glaciation during the Ice Age. And that lasted from about 1 million years ago to 700,000 years ago. The glaciers were never deep enough to totally cap Half Dome. So we had some of these mountain peaks protruded above the glacial ice sheet. If this is your glacier, here's your mountain over here like this. You know, much of it is covered, but the tip tops protruded. And that is an interesting story for a biologist. And this is one of the other things that slowly started to get me interested in geology, because what you find is during the Ice Age, some plants and some animals were essentially stranded on these islands.
Wow.
Does that make sense?
Yeah.
Okay. So there's a term for these peaks that protrude above the glacial ice sheet. They're called nunateks. And nunateks are really a hot topic in evolutionary biology for that reason, because what eventually happened is these glaciers melted out, and these plants were essentially these plants that had co-evolved under these conditions, these Ice Age conditions, to this day are still growing on these mountain peaks. They're basically stranded on these islands. Our park botanist is giving a lecture on Thursday on sky islands. That's another name for these. That's what you'd call these right now. And one of these plants that you can find, if you guys go up to, you're not too far from Saddlebag Lake or Ellery Lake. If you go just outside the park, and you can find this little, it's called an alpine columbine. You guys know what a columbine is?
Yeah, I know what columbine flowers.
Okay, so it's like a purple-white version of that basically grows at tree line and above. So if you walk across the Ellery Lake Dam to the other side, it's probably a little early for them, but you'll see there's this talus in there, these boulders, and they grow right in there. So it's kind of cool.